Hi, this is Brian Fogarty, and this is the video for Chapter 15 of the book Quantitative Social Science Data with R, second edition. And in this video, what we're going to do is run diagnostics on the regression model we did in the previous video, where we were explaining satisfaction in the current political system in Kenya, right, using data from the World Values Survey. Okay, so we're going to run through the battery of diagnostics that we looked at in Chapter 12. So we'll start with functional form. Okay, so we are going to load the Lindia package. Okay, and we are first checking functional form. So gg_res fitted, and then our model 1, that's what we had named it. And then we're going to do theme, BW, again, that's for black and white. Theme, just to make things a little clearer. Okay, I'm going to click zoom and then drag it to make it a little bigger. All right, so we are looking to see whether or not the local means appear to be 0. This is a little tricky to figure out, and a big reason is that our outcome variable only has, 10 values? So this is kind of a weird plot. It's not as nice to look at. Oh, I mean, are residual plots ever nice to look at? So it doesn't appear like it is, but it's because it's kind of weird. I don't have a ton of confidence just relying on this. So let's also run the Ramsey reset test. So we need to load the LM test package. All right, and then it is reset test. There we go. And then we're going to do model 1, comma, power equals 2:3. So again, that is to include squared and cubed versions of the predicted y's as predictors. And then type equals, quote, fitted. Okay, so we're looking here at the p-value, and we see that it is above 0.05. So we conclude that we do not have an issue with functional form. So we don't have to make any corrections. Yay! All right. Let's move on. Next thing is to check for heteroscedasticity. And so we know the answer to this already, to be honest. I'm not even gonna run it. I'm just gonna bring it back up. This definitely has heteroscedasticity, or there's definitely heteroscedasticity. Right, we're looking to see in this plot, is there any pattern? And there's definitely a pattern where it's sloping down. But let's also run the Bush-Pagan test just to confirm that. So we're going to do BP test, model 1, comma, studentize equals false. All right, and we see that the p-value is below 0.05, so we do have heteroscedasticity. So the solution we should use is robust standard errors. We're going to load the sandwich package in order to include the robust standard errors. So we'll do, the function is coef test, model 1, and then vcov equals vcov HC for heteroscedastic consistent. Oh, what did I do? I did something wrong. I'm trying to figure it out. Oh, I typed it, but I didn't load it. There we go. Okay, so we're looking at this, and again, when we run robust standard errors, what we want to do is check whether any of the predictors that were statistically significant in our sort of regular model with non-robust standard errors are still, or if they're not anymore. So looking at this, these are all still statistically significant. So we have the same kind of conclusion about our predictors here. Okay. That's pretty easy. All right. So let's also check normality. Again, so normality, oftentimes we are going to violate it. There might be easy solutions to this, and if there is, then we should use it. If not, then we might want to just ignore it because it might cause kind of bigger issue problems. All right, so let's look at the residuals using the ggres_hist function from the Lindia package. All right, okay, real small. I'm just going to drag that. Okay, so we're looking to see, does it appear like a normal distribution? I'll tell you what, for survey data, this is not terrible, but it's also not normally distributed. All right. We can also look at the QQ plot to see what that tells us. So GG_QQ plot, we have model.1 plus theme_BW. All right, I'm going to click. How did it get smaller? The box. How did the box get even smaller? All right, I'm going to drag it. Again, if it's normally distributed, if it's perfect, then all these dots are going to be on this red line. As is common, we see the tails are off, but especially down here, there is a huge amount that are off here. So again, it appears we do violate it. In Chapter 12, we use the Anderson-Darling normality test. Here, we can use the Shapiro-Wilk that we couldn't use before because it can only go up to 5,000 observations. So for fun, let's use the Shapiro-Wilk test. But it's the same idea as the Anderson-Darling. All right, so we have Shapiro test, model.1, $residuals. Okay. So the p-value is below 0.05, so that indicates that we do violate the normality assumption. All right, so given we violate it, let's take a look at what we might be able to do to correct for it. So we're going to use the Box-Cox transformation. This is coming from the car package, so we want to load the car package. All right, car. And then we're going to do summary power transform. And then our model, model 1. Highlight that, run that. Okay, so we're looking down here. This is below 0.05, so it indicates that we should do a transformation. This is the recommended transformation. And so this number, right, so this says to raise the outcome variable to 0.59. So what I do in the chapter is say, okay, so that's close to 0.5, which is a somewhat intuitive transformation. So I go through and show, okay, let's raise it 0.5, then rerun the Box-Cox, and it shows that we still violate it. So we won't violate it if we use this 0.59. Again, the problem is that it makes interpreting the coefficients really strange. I don't know if really strange, but it makes it difficult. So what we would do is just pass on it. So I talk about this in Chapter 12 and also in Chapter 12 videos about it. So we're just going to punt. We're just going to say, yeah, there might be a problem, so we shouldn't make sort of grandiose statements of what we find here with our sample in terms of whether or not or how or whatever it applies to the general population. Okay. The next thing we're going to do is check for multiclinearity. All right, so we could do where we run a correlation between them. And again, correlation is not like a formal test. It just can give us like a general idea of the relationships here. But let's just cut to the chase and run the VIF test. So VIF model 1, again, we're looking for VIF values of 10 because that would indicate a problem. These are all really low. They're close to 1. So we don't have a problem with multiclinearity. Okay. The last thing we'll do is look at outliers, leverage, and influential data points. So we need to calculate our cut point for leverage. So we have it's 2 times k plus 1. So k here is 8. So we have 2 times 8 plus 1. And then we divide that by n, and it's the n of the model, which is 1105. Okay, so what we can say is that any point that has leverage of equal to or greater than 0.016 has high leverage. Again, a point can be an outlier. It can have high leverage, but it's only a problem if it has high leverage and is an outlier, which is also known as an influential data point. So let's do a plot of all this using the influence index plot, which will do model 1, and then vars equals c, and we have quote studentized, and then hat, I'm going to bring that together, hat, and then cook. Okay, let's click on zoom and drag this. All right. So we do have some outliers, not too bad. What about leverage? 0.16 is here, so there's a handful of them. Cook's distance, I mean, we used the value of 1, but even if we use a smaller value, it doesn't look like we have any problems, right? So like we have 558 is the highest, that's the highest Cook's D value. That shows up as an outlier, but it does not show up as having high leverage. So it's in here somewhere. So it looks like we're good. Okay, so in the text, I take a look at this value, and then say, okay, let's remove it, rerun the regression, and everything's roughly the same. Okay, so what we're going to do then is the only thing we are leaving the diagnostics with is that we'll use robust standard errors. So in the next video, we'll do our interpretations of the coefficients from the model when we're using robust standard errors. Okay, so that's it for this video. Thanks for watching. I'll see you next time.